Hello, welcome to session number 9 in the series Digital Circuit Design using VHDL. My name is Anurag Nigam and I'm talking about FPGAs. Last time I just displayed one uh, output of a JK flip-flop uh, using some form of a prescaler to clock it. So basically the inbuilt frequency here is 100 megahertz, the clock frequency, and at 100 megahertz these LEDs will not respond, right? So for that I designed a prescaler, right? So that prescaler I designed to refresh it, right, at a rate where you can see it, right? So now going forward we often need the 7 segment displays which are on the board, and there are 8 of them, and these 8 of them are common anodes, right? So that means that all the anodes are combined together as a common anode node here. So for 8 LED 8 7 segment displays here, there are going to be 8 controls over here from U13 to J17, right? So when you turn them low, then the current is going to go into the 7 segment display. So basically they are active low, right? And similarly each one of these 8s, right? So basically all these buses of these 8 are tied together, right? Now depending on which one you enable, okay, which one you enable using U13 to J17, that 7 segment display is going to display what is on the data line. So there are 8 data lines from CA to DP. So now if we see the position, CA means cathode A, right? So cathode of A LED, cathode of B LED, cathode of C LED, D, E, F, G, and then DP is for the dot, right? So all these are also have to be, so if you want to turn on a particular LED, that cathode has to be turned low. So that way you can put in any number here. So for example, I can put in a number of 1 if I have B on and C on, right? And if I want 2, I need A on, B on, G on, E on, and D on. Similarly 3, I need A, B, C, D, and G for 3. And for 4, I need F, G, B, C, right? For 5, I need A, F, G, C, D, right? So I can interface my word from left to right, that is left being MSB and the right being the LSB, which is the dot, right? So that is going to be a 4:8. So basically you can display with each digit you can display up to F, right? So you can go from 0 to F. So 0 to F is the hex number, right? So every segment can display one hex number. So that means that 4 inputs can be used to display on one segment, right? So if I have 8-bit wide word, then I need 2 7 segments, okay, 4 for one and then 4 for the other one. So I need a 4:8 decoder, right, to do that. Now I need to refresh, okay. So I need to refresh these 7 segment displays. So what happens is at any point of time only one 7 segment display is working, but I have to turn them on one by one so fast that you have a illusion that all of them are working together, right? And how can I do that? I can use this U13 to J17, and for that I need a 3:8 decoder. Now 3:8 active low decoder for segment refresh. So 3:8 active low decoder means that all the lines of a decoder, of a 3:8 decoder, are going to give an output of 1, but the one which is active is going to be giving an output of 0, right? So we have already done a decoder. We will see how to modify that. So what do we need for this design? Okay, we need a bus which is going to be a data bus, which is going to be 4-bit wide. So why a 4-bit wide? Because I have got each segment can be displaying a 4-bit number, A to F. So that's why there has to be a 4-bit wide data bus. And by the data bus I mean that there are going to be, for that bus there are going to be 8 drivers, and each one are 4-bit wide. 8 drivers because for 8 7 segments I need 8 drivers, and each driver is 4-bit wide. So I need a 4-bit active low output enable buffer for as a bus driver, right, for each one of them. Right, for this 8 digits I need 8 drivers, and each driver is going to be 4-bit wide, right? So that means that I can put a 32-bit word on these 8 7 segment displays. Why 32? Because each one is a 4-bit. So the 8 of them, there are 8 segments, so 8 into 4. So 8 into 4 is going to be 32. So I can represent a 32-bit word on these 8 7 segment displays. So I need a 4:8 decoder which is going to convert a number. So for example, number 1 is going to be B on and C on. So accordingly I need a 4:8 decoder for binary to 7 segment conversion, right? Then I need a 3:8 decoder for choosing which segment is going to be on, right? And I'm going to go cycling it from left to right so fast that you will not notice that I am really displaying one at a time, but it is so fast that your eye has an illusion that I am doing it. I'm doing such that all are working together, but at any point of time only one of these 8 is on, right? So for that I need a 3:8 decoder which is going to drive U13 to J17, right? And also the same input is going to be driving the output enable of the buffers, right? And that also has to be active low, right? So if you do that, you'll be able to display a 8 segment or 8 digit word here, a hex word. Okay, now for running the refresh, okay, I need the 3:8 decoder. I need a 3:8 decoder to be refreshed, right? So that means that will be driven by a 3-bit synchronous counter. Okay, so I'm going to drive with the decoder with the 3-bit synchronous counter. So it is a 3:8. So 3 input, 8 output, right? So 3:8 synchronous counter is going to select which segment is going to be displayed. Okay, then Prescaler for running the refresh counter. So basically this 3-bit counter is a refresh counter, and I need to run it with a Prescaler, because if I do it with 100 megahertz you will not have anything displayed here, right? So I have to do it fast, right? But faster than the Prescale of 26 last time we put for blinking LED. Now I have to do it much faster, so the divide ratio will be smaller. So I would choose somewhere around 22 or 23 or 24, maybe 24 is good number. Then if I see this flickering, then I might increase the speed. So I will start with 24 here. Okay, so I need a Prescaler which is going to be a asynchronous counter which I designed last time. Now the input for this whole module is going to be a 32-bit word, but out of which I'm going to use only 16 of them, and these 16 are going to be connected to the switch, right? So this FPGA has got this switch which is 16 switches are there, right? So whatever I put in as a switch input, that should be displayed on these 4 segments, and remaining 4 segments are going to be 0. Okay, so that's what I'm planning to do. So let's go ahead and design this bit by bit, or rather pieces by pieces, and see how it goes from there. So first thing, what we have a 3:8 decoder, right? So that's a 3:8 decoder which we designed last time. Where is it? Okay, there is the decoder. Okay, now this is a variable size, so I can give n and m. 3:8 is the default value, right? And you can work with any if you want to, but I don't have to make a change here. The only change here I have to make is the output has to be active low, which means all the outputs are high except the selected one which is low. So this is the only change we have to make. We don't make any change in the entity. Entity remains the same. So that decoder, if it is listed here, so let's see if this decoder is listed here. Prescaler. Let's see what is listed in our package. Is decoder listed in our package? Tri-state buffer, mux, adder, half adder, full adder, mux, and we don't have a decoder here. So let's copy that entity and convert it into a component. So all you need is to copy this, Control C, and go into your package and do Control V. Okay, and then turn it into a component. So all you have to do is, instead of entity, you specify component. That's done. Is optional, so I'm going to take it off, and end component, right? Okay, once you do that, you are done. So only thing is I'm going to indent this. Just 1 second. That is so strange. Okay, that's fine. Okay, so that's the indentation done. Even generic, I'll pull it in. Okay, fine. Okay, so that's my decoder. So the decoder portion is done. So where's the decoder? 3:8 decoder for refresh. So I'm going to turn this blue because I'm done with the, or I can say green is done. Okay, next is a tri-state buffer over here. Okay, it has to be 4-bit, but I have designed it to be n-bit, which we have already written, right? So let's just have a look at that. So there is a tri-state buffer here, which is a default 8-bit input, but I'm going to 8-bit input and 8-bit output, but I'm going to use 4-bit. So when I instantiate, I'll keep here 4. The only thing is I want to make it active low. So instead of 1, I'll do the 0. The entity remains the same. So in the package, you don't have to do any change. Okay, tri-state is listed here, I think. Okay, so here a tri-state buffer is listed. Only thing is I'll indent this. Okay, so tri-state buffer is done. Okay, so now I have done that. Now I have to do, let's see if I have done the prescaler. So I have done already the prescaler for refresh. And this is generic, so later on I can do whatever, number I want to put into prescaler. So this is also done. So what do I need next? I need, okay, so of course if I have this is already created. So this I will turn green also. So I need, and this is going to be a 32-bit wide word. So this we'll take care later on. So let's say I want a 4:8 7-segment decoder. Okay, so I am going to do this one. Okay, so I am going to go here and create a new source, a new VHDL file or an entity, and I call this as DEC 7 segment. How's that? Done. And then the library is my circuits, and say finish. Okay, so here I'm going to call this architecture as DEC 7S. Okay, and what is it going to do? It's going to take a 4-bit input word, which is, let's say, A, and this is going to be 3 down to 0, and it is going to give you a Q output. So let's keep them capital. Okay, and Q output is going to be 8-bit. Okay, 7 down to 0. Now here I don't need to do generic because I know it is a 7-segment display. Okay, now this is a common anode, right? So whichever LED you want to turn on has to be 0. Okay, so let's see how do I go about doing that. Okay, so I will go to decoder 7-segment, and I'll get rid of most of this stuff here, and all I will do is I will put this as VHDL code for 4:8 7-segment decoder. Okay, then I want to instantiate anything? No, this is a straightforward design. I don't need to. All I need is write a selected or conditional assignment. Q is assigned something when, okay, A is equal to, so this is kind of laborious, right? So A is kind of A is going to be 0 0 0 0. Okay, else Q is assigned something when A is equal to 0 0 0 1. Else, so all I have to do is I have to just copy this, Control C. Okay, I forgot the, so I'll do a Control C again, Control C, Control V. Okay, so this is for 1, this is for 0 1 0, this is for 2, this is for 3, this is for 4. I can do it another way, but that's going to be the easiest and most efficient inside the hardware. This is when 4, this is when 5, okay, then this is when 6, this is when 6, then when 7, then when 8, when 9, okay, when 10, okay, when 11, when 12, when 13, when 14, uh, 14, and 115. Okay, else I am going to put here, I can put here a high impedance state, or I can put here all ones so that it is off, right? So all ones I can put for this to be off. I don't want to keep a high impedance. Okay, so all ones, right? So here 8 times I will introduce 1, 4, 5, 4, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so when I do this, it's going to be off, right? So that's the statement which will code it. Now let's fill in the numbers. Okay, so the first number is for A. So if I do 0, A is 1, B is 1, C is 1, D is 1, E is 1, F is 1, G is 0, H is 1. So basically I have written it opposite. It's a common anode, so this is a cathode, right? So A is 0, B is 0, C is 0, D is 0, E is 0, F is 0, G is 1, and DP is 0. So that is going to represent 0. Now if I was to write 1, okay, so A is 1, B is 0, C is 0, D is 1, E is 1, F is 1, G is 1, and DP is 1. Correct? Now if I was to write 2, then A is 0, B is 0, C is 1, D is 0, E is 0, F is 1, G is 0, and DP is 1. Correct? So this is going to be, if there is a problem, we will correct it. Okay, so this is going to be 2, isn't it? A0, B0, C1, D0, okay, E0, F1, G0, and DP1. Fine. So now for 3, A is 0, B is 0, C is 0, D is 0, E is 1, F is 1, G is 0, DP is 1. Okay, so this is for 3. Now for 4, I'm going to have A as 1, B as 0, C as 0, D as 1, E as 1, F as 0, G as 0, DP as 1. So this is for 4. Now for 5, I have got A is 0, B is 1, C is 0, D is 0, E is 1, F is 0, and then G is 0, DP is 1. Correct? And for 6, I have got A as 0, sorry, A as 0, B as 1. So A as 0, B as 1, C as 0, D as 0, E as 0, F as 0, G as 0, DP as 1. This is 6. Now this is 7. For 7, I have got A as 0, B as 0, C as 0, D as 1, E as 1, F as 1, G as 1, and DP as 1. Okay, now let's see 8. For 8, all of them except DP is going to be 0, right? So it is going to be A is 0, B is 0, C is 0, D is 0, E is 0, F is 0, G is 0, DP is 1. Okay, now for 9, I am going to have A as 0, B as 0, C as 0, D as 0, E as 1, F as 0, G as 0, DP as 1. Okay, for 10, which is A, for A, you have got A as, A as 0, A as 0, B as 0, C as 0, D as 1, E as 0, F as 0, G as 0, DP as 1. So this is going to be A. For B, I'm going to use a small, instead of capital, I'm going to use a small b, right? So A is going to be 1, B is 1, C is 0, D is 0, E is 0, F is 0, G is 0, DP is 1. Okay, so now for C, I have got A as 0, B as 1, C as 1, D as 0, E as 0, F as 0, G as 1, DP as 1. Okay. Now for now we were where? We were at C, right? Now D. For D, I want to make a small d because I don't want to confuse uh, with 0. So in that case, A is 1, B is 0, C is 0, D is 0, E is 0, F is 1, G is 0, and DP is 1. So this is D. For E, I have got A as 0, B as 1, C as 1, D as 0, E as 0, F as 0, G as 0, DP as 1. Okay. Now for F, I have got A as 0, B as 1, C as 1, D as 1, E as 0, F as 0, G as 0, DP as 1. Okay, so we have done the 4:8 decoder, which is just a simple display, right? So I'm going to save it, and I am going to just make a component out of this. Okay, so I'm going to copy this, Control C, and I'm going to paste it here, Control V. Okay, so this part was very simple. And end of component is optional. Okay, so we are done with the decoder. So let's go back to our this thing. So we are done with 4:8 decoder. Okay, so all I need now is a 3-bit synchronous counter. Okay, so let's design a synchronous counter using T flip-flops, right? So where is it? Here. So let me see, am I recording? Yes. Okay, so I need to go here and make a synchronous counter. So I will add a source here and say next and say create, and here I'm going to say sync count, okay, n bit. So I'm going to write a generic sync count n bit. Okay. Oh, okay, and then this is going to be my circuits, and then let's do the architecture and say s count, sorry about this alarm, s count n bit. So this s count is good enough. So what do we need as a input to this counter? Okay, so all you need is a t, and then you need a clock, then you need a clear, right? Clock t, clock clear, and what else do you need? And you need an output which is going to be n bit wide. So to start with, let's make it a 7 down to 0. Okay, so this is going to be a n bit counter. Is that correct? Yeah. Okay, so there it is. Okay, so this is a VHDL code for n bit synchronous counter, and here let's get rid of this, and here I need library my circuits, and then I need use my circuits package.r. Okay, so that's done. Now I don't ripple it, okay, but I still need the intermediate one, right? So I need, okay, first of all I need to put in a generic. So I'm going to put here generic. Then I'm going to say this is n bit integer, and this give it a default value of 8. Done. Right, and then here I'm going to do a signal, and I'll call this as W only. Okay, and this is a std logic, std underscore logic, and I'm not going to show overflow with this counter, right? So that means that I just need a vector which is going to be n minus 1 down to 0. Correct, and q is also n minus 1 down to 0. Okay, so first of all I have to set right the t logic, right? So the t logic is I want to give W0 as t, correct? So W0 goes as t. Then I'm going to say for I, so I have to do a generate, so I have to name the loop. For I in 0 to n minus 1, correct? Generate, and generate LP1. So that's how I'm going to end the generate loop. And here okay, here I need to have the T flip-flops, right? So before that, okay, so let's see how I approach this. Okay, let's see how I approach it, because the output is going to be with the W0 and output will be Q0. So I will be generating W1 every time, right? So if I was to generate WI plus 1, okay, is assigned WI and with QI. That's going to be the T input for the next one, isn't it? So why is it red? Ah, okay. So I cannot use this one, right? So I would have to introduce another one, WU, for example. Okay, U is okay. So I don't work with Q, I work with UI, correct? So what does it mean? It means that it will go up to 1 bit extra, right? So it will go, when it goes to n minus 1, then this will become Wn, and Wn doesn't exist, right? Wn doesn't exist. Okay, So I can do two ways. I can either have a W which is n2 down to 0, or another approach is run this loop to n minus 2 and then instantiate n minus 1 separately. Right. So here I am going to say TF1 is a T flip-flop. Sorry. Is a T flip-flop port map. And in this port map, I'm going to look at the entity of T flip-flop. Okay. Where is T flip-flop? Here it is. T clock clear Q. T clock clear Q. T, which is going to be WI. Clock is going to be clock. Clear is going to be clear. And Q is going to be UI. T clock clear Q. That's fine. So every time it is generating the T input for the next one. And when you are done with this, you would say W n minus 1 is assigned W n minus 2 okay, and with U n minus 2. Right, so this will generate the, so hang on a second. So this is going to n minus 2. So this is generating, it is generating already W n minus 1 using n minus 2, but I haven't saved it anywhere, right? But this is generated, so this will be a restatement, isn't it? Okay, so it is already assigned inside here. W n minus 1 n W I minus 2 or I minus 1. W I minus 1 is equal to W n minus 1 is equal to W n minus 2 and with U n minus 2. So it is already done. So all I have to do is TF2 is going to be a T flip-flop. So I hope you understand how I'm accommodating the last one. Okay, I don't want to leave a floating pin inside. That's why I didn't take Wn down to 0. Okay, so here you are going to have Wn minus 1 created, comma with the clock, comma with the clear, comma with the U, and this is going to be n minus 1. Okay, so this is the last flip-flop. So W is populated completely and U is populated completely. Un minus 1 down to 0. Right. So the last step is Q is assigned U. Right. So I'm done with this synchronous counter, which is 8-bit wide, and I am going to run it because I'm not sure if it is working. So I'm going to set this as a top level module. So I'm going to set this as a top level module, and then in the settings I have sync counter. For simulation I should also have sync counter. Okay, and say OK. So now I'm ready to simulate this 8-bit synchronous counter. So if T is high, it is going to toggle. If T is low, it is not going to toggle. If clear is high, it is going to be 0 0 everywhere. So just run this simulation. Due to errors. Okay, elaborate step failed. Okay, let's try to see what happened. Because errors are part of this training. Message spawn failed. Okay, spawn failed. Usually spawn fails when CKTS is not compiled before. Let's try this again. Okay, so let's run this again. It says 9 errors. Simulation failed due to errors. Elaborate step. Okay, I'm going to put you on a pause and try to fix this. Okay, so the problem is there is a constraint when we were testing JK. You have to go and disable this. So you can right click and say disable file instead of enable. So if it will be enabled, you have to disable. So right now my configuration file will not match. Second thing was this T flip-flop was somewhere modified and it had to be resaved, and that's why it was giving an error. Right, so now let's go back to our synchronous counter. I haven't made any changes to it. No changes to it. It's a synchronous counter. So here what I'm going to do is I'm going to run the simulation again. Okay, so the problem was T flip-flop got modified. So I'll go to simulation, run behavioral simulation. Okay, so it is done. So I am not interested in W and U and neither in N. So I'm going to delete it from here. I'm going to reset this. Okay, first of all, I'm going to set T as 1, forcing T as 1. Then I'm forcing clock as a clock. Force clock with a leading 1, trailing 0. And then I am going to have a clear as high because the initial state is not defined. So clear is high. So if I do this and I simulate for 100 nanosecond, so I have 0 0 set as the initial value. Okay, so output of this counter is 0 0. Now I'm going to enable the clock. So basically I will bring down the clear. So I'll make clear as 0. Now the toggle is on already, right? The toggle is on, the clock is on, and let's simulate for, let's say, 100. So I will do 1600. Okay, and say simulate. So once I simulate 1600, I'll want to see what has happened to my waveform. So I'll say view all. So it counted up from 1 2 3 4 5 6 7 8 9 10, or 0 A B C D E F 1 0. Okay, if I do this for another 16, I'll reach 2 0. Another 1600, I will reach 3 0, 4 0, 5 0, 6 0. So counter is working fine. Now if I hold the T to be low, the count should be frozen. So I will force T. So this is over here. I'm going to force T as 0. That means I'm not toggling it. And if I click run, it has maintained 7T, right? So you can see wherever it turned from 6F to 7.0, it has maintained 7.0 because the toggle is freezing the toggle. And same thing is if I was to force clear to 1 anytime, because this is asynchronous, it will immediately turn to 0 irrespective of the clock. So irrespective of the clock, the output has turned 0 as soon as you bring in clear. And if you take clear off, it will start counting again provided T is high, right? So if I take clear off, it will start counting provided T is high. So force T also, T is high. Okay, so it will start recounting from 0 0. So it has recounted from 0 0 to 1 1 0. So again in 16 states it has recounted. So so synchronous counter is working. So I'm going to close the simulation waveform. Discard the changes. Okay, so here we were. So we got all our blocks done. So let's see. So we have got the synchronous counter done also. Okay, so now I want a module, or rather a component, which takes a 32-bit word and it's just going to give a out. Okay, so it's going to take 32-bit word and going to display it over here, right? So I want one module like that. Okay, so let's see. I have synchronous counter. I am going to copy this and make it a component. Control C, and under circuits, Control V, and this one is a component, component, and this would be N component. Right, indent this properly, and similarly this one and this one and this one. Okay, so we are done with the package and we have everything in place. Now I want to create a new code which is going to create the entire thing. All you have to do is to give it a word, okay, and it is going to do the job, right? Okay, so let's do that. So I want to add a source and say create a file segment, okay, digit 8 display. How's that? So I'm going to do a 8-digit display, correct? And the library is my circuits. Architecture is digit 8 segment. And what does it require? It requires just the clock and a 32-bit input. Rest it has to manage on its own, right? But okay, so it needs a 32-bit input, so this will be a word in, and this will be 31 down to 0, correct? And then it has to give me out a control signal, CNTL, sorry, CNTL. It has to give me out a control signal, right? And that will be a out, and there will be 8 control signals, okay, 7 down to 0, correct? And then we also need data. out. So D out, it's also going to be 8-bit, isn't it? Yeah. And it needs a scalar clock in. So it needs a T. So it needs a T. It needs a clock. It needs a clear. These are all scalars, isn't it? Okay. 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 So this will be a display, right? 8 digit 8 display. Okay. This is the last thing which I'm going to write and then instantiate and run it. So let's see if I am recording this. Oh my god. Okay, so this is a VHDL code for 32-bit display. Okay, and then it is going to use your my circuit stuff, right? So I need the library to be defined here. Library my circuits, correct? And then use my circuits.all. Okay, and then I need, okay, so I have a word in which is a 31 down to 0. Then I have got control and D out is the output, T clock clear as the input. So let's start instantiating it. Okay, so first of all I need a bus, correct? So I need a bus, so that will be a signal, right? It will be a signal, and this is going to be a D bus, std underscore logic underscore vector, and this will be 4-bit wise, so it will be 3 down to 0, correct? So that's the bus. Let me see if I'm recording it. Yes, I am. So I have a bus, then all the outputs have to be placed on that bus, right? So there are 8 digits, right? Okay, so each one is going to be placed on this, output is going to be placed on this bus, and these outputs are going to come from word in. So before that I need a decoder here, correct? And before the decoder I would need a counter, and before the counter I would need a prescaler. So first thing I would need is a prescaler. So I want a pre1, which is a prescaler port map. Okay, and generic map, generic generic map, and I have to give it a generic map. So let's say this is a refresh, so I'm going to start with 2024, right? So that's the generate map, and then the port map. So I need to see my circuits here, circuits. So in circuits I have a prescaler defined. Where is it? Prescaler generic map 24, T clock clear clock out, T clock clear clock out. Okay, so I need clock out, signal clock out is a std underscore logic. Okay, so T is the T input, clock is the clock input, clear is the clear input, and then clock out is the clock out. Correct. So now clock out has received the scale down frequency from the prescaler. Now this is going to drive the synchronous counter. So I will say sync 1 is a sync counter n bit, and then this one has a generic map, and this is going to be 3 bits, so it is going to be 3 bit wide. Then is going to be a port map, and here I have to see the synchronous counter port map. So generic map is going to be 3 T clock clear Q, right? And Q is going to be 8 bit wide, isn't it? Right. So this is going to be 8 bit wide output. So here I'll generate signal, and this signal is going to be DEC out std underscore logic underscore vector, and this will be 7 down to 0. So this one is going to be the output. So if you go to decoder, so synchronous counter, and you also want that to be driving, right? So you also need one more 3 down to 3 bit, right? 2 down to 0. So that will be DEC in. Signal decoder in is going to be 3 bit wide, std underscore logic underscore vector, and this is going to be 2 down to 0. Correct. And this is a synchronous 3 bit wide, and its output is T clock clear and Q. T clock would be clock out, which is prescale, clock clear, and your output synchronous counter output is going to be decoder input. Correct? So what's the problem here? Okay, sync count counter n bit. So let's see what is it defined as, if not this. Okay, sync count n bit. So I'm just going to copy this, because sometimes name plays a havoc. Control C, and here this is named improperly, Control V. So now this is okay. So now I have instantiated a synchronous counter, which is a 3 bit counter, which is giving an input to the decoder, right? Now I need a decoder 3:8. Okay, so this will be called this. Okay, Control C. I don't want to do a spelling mistake again. So this would be called decoder, and I have to give a GENERIC. This is optional. this is 3 comma 8. Okay, so this is optional because n 3 comma 8 is already provided here. Okay, and then do a port map, and in this case the port map on the output is going to be, input is S, output is Q. So DEC in and DEC out. Okay, so DEC in and DEC out. DEC in and DEC out. And this is a decoder instantiated. Okay, so now I am done with that piece. Now I need to make a bus. So DEC out is a 8-bit wide, right? 7 down to 0. Correct? Okay, so now I need to create buffer, tri-state buffers. Okay, so there will be 8 buffers, right? So I can say LP1 is a for loop. Okay, for I in 0 2, and how many are there? 7. Generate. So I'm going to generate and generate, and this is going to be LP1. Okay, okay, so now I have to generate a tri-state buffers. Okay, so let's look at tri-state buffer. It is going to be generic 8. So let me just copy the name of the entity. Control C, Control V. Okay, that's the entity. Then I have to put generic map. Okay, so tri-state buffer, they are going to be 4 buffers, 4-bit wide buffers, right? Tri-state buffer, this is going to be 4-bit wide. Okay, so this is going to be 4-bit wide. Then do a port map. Okay, for a tri-state buffer I need to see I output enable and Q. I output enable and Q. Okay, so it will be word in, right? Word in. I is going to be word in something. Okay, then OE, output enable. Output enable is 0 to 7, right? So that is going to be the decoder 0 to 7, isn't it? Right? And decoder out has to be available to the output also, right? As a control. Okay, so decoder out, DEC out, this is going to be output enable I. So that particular decoder is going to be enabled. Then it has to be out. Out is going to be a D bus, right? Out is going to be D bus. Correct. So this is simple. D bus. Okay. So now what's the problem? The problem here is this one is going to be a word which is going to be I times of so this is 4-bit, right? So it is going to be I times of 4. So it is going to be okay, I times of 4 minus 1 down to I times of 4. So let's see, if I is 0, then it will be, so this will be wrong, right? Zero to 7, right? So let's generate this logic. I times of 4 plus 3 down to I times of 4. So this will be 3 down to 0. Now when I is 1, then 4 plus 3 is 7 down to 4. 7, 6, 5, 4. Right? Then it is going to be I equal to 7, for example. So 7 4 is 28. 28 plus 3 is 31 down to 28. 31, 30, 29 and 28. And this is going to be having an output enable as DEC out 0, and this is putting this on a D bus. So at any point of time, that particular segment will receive the data on this D bus. Correct? Okay, so that will receive data on D bus, and it is going to be multiplexed by the decoder, whichever data is placed, and that decoder is also generating the controlled output, right? Okay, and now I need a 7-segment decoder, isn't it? 4:7 segment decoder, so which will take the D bus output. So there will be a 7-segment decoder. Okay, Control C, and this is only out, unlike the control, so I can directly give it to the output. Okay, so I will say segment decoder, and I only need one decoder, right? So that would be that, and it is going to receive D bus as the input, and it is going to directly give the output, will be the 8-bit wide output, D out, isn't it? Yeah, D out. So let me just check its entity. A input, which is 3 down to 0, and 8-bit output, which is D out. So why is it complaining? Ah, port map. So this is going to be, sometimes I do a stupid mistake. Okay, port map. So that is the D out. So D out has reached its output. Now only thing is the control output. So T is utilized, clock is utilized, clear is utilized. Word is in is totally utilized from 31 down to 0. All I need is a control output. Okay, and this output basically is generated as DEC out. Oh, I did a mistake here. Why did I put this inside the generate block? It's not inside the generate block. It is outside the generate block. Correct. And here I need D bus and D out is done. Control CNTL is assigned the decoder output. CNTL is the DEC out. DEC out. Well, you know, I have coded this, but I'm not sure if this is going to work. Correct? So I'm taking a 32-bit input. So again, I will have to do a test bench. Okay, test display, where I am going to put in 16 of those 32. So I'm going to fill in this word from 31 down to 16. I'm going to fill this with 1 width. So I want to display nothing, right? So I want to display 0, for example. So I'll put them with zeros, and then 16 to this as input switches. Okay, so I'm going to generate a test bench. Okay, so it might require debugging because I'm not very sure if I'm doing everything right. Okay, so I am going to go here and add a source and say next and say create file and call this one as test display. Correct? And it is in the same library, and say finish. And this test display, okay, test dip. Okay, and this one is going to take 16 word input. Then it is going to have T, clock, clear as scalars, and then it is going to take in, now there is a issue here, T, clock, clear. Okay, how would I freeze it? Because among the switches I have only 16-bit inputs, right? So I will keep toggle as normally on because I really need not pause it, right? Only clear I will give in. Only clear I would give in, right? Okay, as one of the switches. That's fine. Okay, so then I am going to give word in. This is going to be 15 down to 0. Okay, and then I have to have control, which will be control. This is going to be output lines, and these are going to be 7 down to 0. And what about the data, which is going to be D out, is also going to be 7 down to 0, isn't it? Fine. Okay, so let's see where is this created. What is it doing? Okay. Why is this instantiated out here? I don't want to see this. So why is it showing me this? LP1, LP2. What happened to my hierarchy? Why is this instantiated here? Tri-state buffer, how many times is it instantiating? 7 times. What happened to my tri-state buffer? It should be under display, right? Display. Let's check this. That's not making sense to me. I am generating tri-state buffer here inside that. So why can I not shrink it? Oh, because of that. Okay, so this is going to be a top level module now. No. Test display. Okay, so this I'm going to write. This is going to be my top level module. Okay. So I'm going to put here test display. Come on. VHDL code to test 7 segment display. Correct. And then I haven't taken this one. I should basically take this and put it in the package. Control C, because everything else is in the package, only this one is not. So let's put that in the package. Control V. Indent it properly. Make this a component. Is optional. Similarly here is optional. And component. Right. And here I'll just indent this. Okay. This is done. Fine. So we are ready to write the test display. So I'm going to instantiate that. So I'm going to say library my circuits. Okay, it doesn't make a difference though. My circuits use my circuits.all, correct? And here I am going to give input, right? So I need a 32-bit word. So I'm going to say signal WRD is std underscore logic underscore 11 underscore vector right? This is 31 down to 0. This is a 32-bit word, and out of this word is assigned 31 down to 16. This one I want to assign all zeros. Okay, does this work? I'm trying everything new here. I can't fill it with zeros. Double assignment is not possible. Let me put you on pause and try to figure this out. Okay, so it was very simple. Word 31 down to 16 is other 0. Then word 15 down to 0 is assigned word in. Word in. Okay. Isn't it? Correct. So my word is filled now. Then T clock clear is to be assigned. Control and D out is the output. Okay, so this is very simple now. I have to instantiate this display. Okay, so I'm just going to copy this. I don't want to make mistakes. So I'm going to say dip is going to be this. So I am going to instantiate this guy, and here I'm going to say port map. Okay, so first is the word in. So in this case, the word in is going to be WRD. Right. Next is going to be control. So this is going to be control and D out. CNTL and D out. Is that correct? CNTL and D out. Okay, so CNTL and D out is done. These are my outputs. Then I am going to have T clock clear, right? T clock clear is coming from the inputs, right? Okay, T clock clear. And we are done with the instantiation. And this part goes off. Okay, so now I have instantiated this, okay, which is going to receive T clock clear. Now here clear I need, but the clock is going to be the same 100 megahertz input, right? So this clock is not a physical pin which I have to define. As far as T is concerned, T is always going to be 1. So always toggle it. So no issues with that. So I am going to require control and D out, which is going to go to FPGA. This is going to coming from FPGA going to those particular pins, right? So this is generating that. It's a output, right? Which is going to control these LEDs. And word is my 16 of them is coming from my word in, which is going to be the pins, right? And then clock is coming in from E3 and clear is coming on from one of the words. So the initial state is a confusing state, but it's okay. We will just have push button. That's okay. So now we are done with this, and let's set this as a top level module. Okay, so this one is a top level module. Okay, so now this is going to be crazy because this is too elaborate, and the reason for showing you all this is, do I need this? Oh, why messages is over here? Shouldn't the messages be here? Okay, so the reason, so I have a constraint which is disabled, or I can delete this constraint, isn't it? Remove the file from the project, fine, and empty this constraint out. So can I just press delete? No, constraint 1 will always stay there. It's okay. Okay, so let's look at the settings. I am not going to do any simulations, but still test display. Okay, general is test display. So this is all set, and so we are okay with this. Now I am going to do run synthesis. Okay, this is crazy, guys. Okay, but you know, this is what is required to display it. So if it works well and good, then yeah, otherwise you have to do a lot of debugging. Okay, so let's go here and run synthesis. So fingers crossed, I'm going to put you on spawn error. Don't worry about spawn error, it's still running synthesis. Okay, I'm going to put you on pause, and if anything falls out, I'm responsible, I'll correct it. So let's put you on. Okay, so welcome back. So let me tell you what happened. Okay, in this 4 to 7 segment decoder, I had to put a 1 here. Earlier I had put a 0 here, so that dot was coming on with the 0. Okay, so I have corrected that. B, my refresh rate has to be increased, so I have a generic map. I had put here 24. Now I'm putting 17, so that you know the all the 8 digits are appearing at once, right? So that's the only changes which I have done. After that, I ran the synthesis implementation, generated the bit stream already. Okay, so I have generated the bit stream already. Right now the device is running, so built-in self-test, right? So let me put this on a full screen. Okay, so before that, let me just do the following. Let's go ahead and open the hardware manager. Okay, then open the target, auto connect. Right, I hope you can see it. Let me verify if you can see my device. Yes, you are able to see, right? It's running built-in self-test. Okay, let's see, where are we right now? Okay, so I have to program the device. So I program the device. Okay, by the way, I in between I had put the constraints, so I'll show you later on. So let me put it on a full screen now. Okay, function F12. Okay, so what you see here, it's displaying 0 0, right? Because you know uh, the first 4 of these are zeros anyways, because we are going to not receive any inputs for these 4. then the remaining 4 I'm going to receive the input from these 16 switches, right? And this is a clear. So this basically is going to clear the prescaler, right? So prescaler, which is driving this multiplex display. Okay, so now let's do few things. Let's put in 1. So you see that the first 4 bits are going to be your first segment. So this is 1, this is 2, sorry, this is 2, so this is 3, then this is 4, then I can generate a 5, then I hope you can see that, right? Then I can generate a 6, then a 7, then if I bring all this down, 8, then a 9, then a sorry, so this switch is messing up, so this is A, then I have to generate a B, right? So this is going to be B, then I have to generate a C, then I have to generate a D, then I have to generate a E, and then I have to generate a F. So the data lines are working fine because it is multiplex, so I need to just confirm these 4, remaining whatever you want to put. So for example, I want to put 2A, so this is going to be 2, and then the next 4 bits I am going to put A, so this is A, and then I want to put 3C, so this is going to be 3, and I want to put C, so this is okay, this switch is loose anyways. So 2A 3C, so I have put 2A and 2A and 3C here, right? So to be clear, let me bring it closer, and hopefully you can see now I am putting through switches. Okay, so you can see the switches here. So I have put 2A, okay, I have put 2A and 3C, right? So this switch is messing up a little. Okay, maybe some dust or something. So 2A 3C. So you can see I can do a multiplex display. Now if I want to make an adder or a multiplier or anything else, I'll be able to see the display over here, right? So that's there. So again, you can clear your what you call the clock or the prescaler by this switch. So now where are these constraints? So again, kind of I jumped ahead. So when I show you window, okay, so let me close the hardware manager now. Close the hardware manager. Okay, let me go back to showing you my screen. Okay, so I have closed the hardware manager, and now I want to look at the I/O window. I don't see that, so let me see if anything is open. No, so it should be somewhere here only. It should be under Windows. It should be I/O constraints. Okay, cancel. Let me open a synthesized design. Okay, let's look at the I/O ports. Okay, so now you see here, these are my 16 inputs. Okay, so these 16 inputs are basically the 16 switches going from V10 all the way down to J15. So they go from V10, over here you see V10 to J15. So this on the left hand side you can see these switches. So these switches are the 16 inputs. Then then you can see the data word. Okay, so this is the data word. So this is going to be 8-bit wide. correct, and it goes from T10 to H15. So T10, you can see here T10 to H15. These are the cathodes, cathode A, cathode B, cathode C, D, E, F, G, and DP. So this is T10 to H15. So that's over here constraint T10 to H15. Then going further up, you have got the control. Control is again for the 8 common anodes, right? For the 8 displays. So they go from U13 to J17, right? So they go from U13 to J17. So now you see that putting all this together, okay, putting all this together, we get this display. Now, of course, you know, you may say that this is too much of a work, but then even if you use something ready-made, somebody has taken pains to do this, right? So as we go further, the designs will become more and more complicated. So when I show you the data path of a processor, it's going to be much more complicated than this. So this is just a display, right? So I can run a counter also on this 7-segment display here. But anyway, so I am going to stop here, right? And hopefully it makes sense to you now. Okay, thanks a lot. Thank you.